Okay, let's continue. So we were proving this theorem, and I described you the idea. Now before we try to construct whatever map we're going to construct, let's first make sure that we understand that these 3 bullet points are mutually exclusive cases. So you see, I put either there. So either this happens, or this happens. So this is an either or statement. So these cannot happen at the same time. These are mutually exclusive cases. Let's understand that. Now, these cases are mutually exclusive since otherwise we would have a well-ordered set that is isomorphic to a proper initial segment. That is isomorphic to a proper initial segment of itself, okay? Proper initial segment of itself. Why? Let's say that these two happen at the same time, okay? So P and Q are isomorphic, but P is also isomorphic to an initial segment of Q. So this is isomorphic to an initial segment of Q, but it's also isomorphic to Q. By composing the inverse of this isomorphism with this one, Q is then isomorphic to an initial segment of itself, which is impossible. If these two happen at the same time, then P is isomorphic to an initial segment of itself, which cannot happen, and these two cannot happen, otherwise P would be isomorphic to an initial segment of itself. So if you assume that any two of these guys happen together, then you would have a well-ordered set which is isomorphic to a proper initial segment of itself, which is impossible, okay? By the corollary we proved earlier. Thus, these are mutually exclusive. Now, in order to show that one of the 3 cases hold, consider the following relation. Remember, like we observed on this picture, that if there is to be an isomorphism, if we are to find an isomorphism between these two guys, that isomorphism should send an element to this. It should send this element to this element whenever these predecessors are isomorphic. These predecessors are mapped to each other. So we're going to use that idea to construct a map. So what are the names of those guys? P and Q. So I take all ordered pairs A, B such that predecessors of this guy with the restricted relation, maybe I should write this, is isomorphic to predecessors of this guy with the restricted relation. So an element here is mapped to an element here if the predecessors of these guys as well-ordered sets are isomorphic. Now, this is obviously a relation. This is a set of ordered pairs satisfying some property. We first show that this relation is actually a function. We first show that f is a function. Assume not. Then how can f be not a function? There exists B and C in Q and A in A in P such that how can f be not a function? it's not supposed to be well defined. So you should be able to find two distinct elements of Q, let's call these B and C, such that there is some A which is mapped to both of these guys. Now these guys are different, which means that because we're working with a linear order, I mean this is a special kind of linear order, we have that B is less than or equal to C or C is less than or equal to B. Okay? And so C is an element of predecessors of B, or B is an element of predecessors of C. Moreover, we have now, when is A map, like when is an ordered pair in this relation F? If predecessors of A is isomorphic to predecessors of B. We have this if predecessors of A is also isomorphic to predecessors of C. The isomorphism relation is, the order isomorphism relation is transitive, meaning that if these are isomorphic and if these are isomorphic, then these are supposed to be isomorphic as well, because when you compose two order isomorphisms, you also get an isomorphism, order isomorphism, okay? So in particular, B and C are, predecessors of B and C are isomorphic. But then this or this other set is isomorphic to a proper initial segment of itself, okay? Proper initial segment of itself, which is a contradiction. Why is this true? Let's understand this. This is my well-ordered set Q. This is my B. And let's say that C is over here. Let's say that we are in this case, okay? Let's say that C is less than B. I know that predecessors of B and predecessors of C, these are isomorphic. So this well-ordered set is isomorphic to this well-ordered set, but this is an initial segment of this, so, and C is different than B, so a well-ordered set is isomorphic to a proper initial segment of itself, so we have a contradiction. Now assume that we are in this case. Still, the same thing is going on. These guys are isomorphic. So predecessors of C is like this well-ordered set, this well-ordered set is isomorphic to this well-ordered set, which is an initial segment of this one. So we contradict the fact we proved earlier. Thus, this cannot happen. F is indeed a function. Okay? Thus, F is indeed a function. Now, a function, when I say a function, I simply mean it's a well-defined relation. Now we're going to understand the domain and the range of this guy. There are three cases that can happen. The first case, the lucky case. The domain of F is, exercise. I'm going to assign an exercise in the middle of the proof. Show that this F is order preserving. Show that F is order preserving. The proof of this is simple. Again, you're going to contradict, like do this with a contradiction. This by assuming that it's not order preserving. If you assume that F is not order preserving, you're going to again have a well-ordered set which is isomorphic to a proper initial segment of itself, okay? So it's not difficult to do this. Now, I have a function from a subset of P to a subset of Q, and it is order preserving. Let's understand the domain and the range of this guy. There are three cases. The lucky case. The domain of this is P and the range of this is Q. In this case, this is an order isomorphism. Okay? If the domain of F covers all of P and if the range of F covers all of Q, then I have a bijection which is order preserving. Why is this a bijection? You see, when this is order preserving, the one-to-oneness automatically come, right? So, or you can actually directly prove that this is one-to-one. Switch the places of these. Assume that BA is in F and CA is in F. Switch the places of all these letters in this argument. You're going to run into the same contradiction. Assume that F is not one-to-one. You're going to run into the same contradiction. So we have this guy. So prove that F is order preserving. So we have an order preserving bijection between P and Q. So it's an isomorphism. So we're in the first case. Now, let's say that this does not happen. Then either this does not happen or this does not happen. Okay, so let's cover those cases. Case 2. Let's say that the domain of F is not P. Okay. Yeah, I don't want something else over there. Yeah. I should have proven a lemma before this, but whatever. Okay. No, I will do that. So that's the lucky case. Before the unlucky cases, let's prove a small sublemma within this proof. The domain and range of this function are initial segments of P and Q respectively. Then after this lemma, we're going to go into the second case. Let's prove this. Let me just do the proof for the domain, and the proof for range is symmetrical because you're just going to flip the places. Now, we prove this for domain of F. Now we want to show that this is an initial segment. What is an initial segment? It's supposed to be closed under predecessors, meaning that if I take any element, the predecessors of this guy should be a subset of this. We wish to show that the predecessors of this guy is a subset of domain. That's what it means for domain of F to be an initial segment. Now, let A prime be an element of predecessors of A. Okay? Let B be the element such that f of A is B, okay? So let me use this part for picture. I have some relation which relates certain things from here to here. Let's say that this is the domain of F. I want to show that this is an initial segment. So I chose some element A in here. I want to show that its predecessors are also in domain of F. Now this guy is mapped to some guy. By definition of F, the predecessors of A is isomorphic. By definition of F, there exists an order isomorphism. Let's call it G, from predecessors of A to predecessors of B. Because in order for A to be mapped to B, their predecessors should be isomorphic. So let's say that they're isomorphic via this element G. Then, if I restrict this, now, the predecessors of this guy is isomorphic to predecessors of this guy by some G. If I restrict this G to the predecessors of A prime, then it will be, if I restrict this G to the predecessors of A prime, this will be an order isomorphism. This needs to be proven, but I don't want to do it. From predecessors of A prime to predecessors of B prime, where B prime is, you can guess, G of A prime. Okay? So this guy, this A prime is mapped to some element B prime in here. So the predecessors of this guy is isomorphic to predecessors of this guy via this G. And so I have an order isomorphism between predecessors of this guy and predecessors of this guy. By definition, A prime is mapped to B prime under F. Okay? Thus, we have proven this. Predecessors of A is a subset of domain of F because we took an element of we took an element from predecessors of A. It's a subset of, it's an element of domain of F. So I proved that. And that finishes the proof that this is an initial segment. Is an initial segment. Now the proof for the range is it's symmetrical. You just do this except you change the order of things. The proof for the range of F is symmetrical. Just do this as an exercise, okay? You're just going to flip everything. Questions about this? So,
is it a part of the proof?
What?
Is this a part of this proof?
Yes. This is like a sublemma of this proof. Now we have that the domain and range of this function are initial segments of P and Q respectively. case 2. We can now continue to the second case. Domain of F is different than P. And the third case is range of F is different than Q. Or why am I doing it like this? Okay, never mind. Okay. Do I want that? I want the other one. Let's assume that the range is not Q, okay? That's better. Okay. As range of F is a proper initial segment of Q. If I confuse it, let me just go over this. If we are lucky, then the domain is all of P, then the range is all of Q. Let's say that we're unlucky. Let's say that the range is not all of Q. It can happen. Now, this is an initial segment. It's a proper initial segment, so it has to be the set of predecessors of some element. So the range of F is, let's say, B for some B. Now, what I'm going to do is the following. I need to draw some pictures. I have this F. Let's say that this is the range. The range is not the whole thing. Because it's an initial segment, it's the predecessors of some element. Now, I'm just going to pull back this range by F, okay? Since the domain of F is also an initial segment, note that this is also an initial segment. We just proved that. If it were proper, let's say that if it's the case that this is not all of P, then because it's a proper initial segment, it's also a set of predecessors of some element for some A in P. Okay? You see, for some reason I tried to change the proof I wrote in the notes. So I might have confused it because I couldn't decide whether to follow that or to do my own proof, which I had at the beginning. So I might have confused you. So let me go over this. We are assuming that the range is not all of Q. Why are we assuming this? Because take the negation of this. Either this doesn't happen or this doesn't happen. So let's go into look at the case. This doesn't happen. The range is not all of Q. Then, because this is a proper initial segment, we have some B such that this is not obviously B. It's predecessors of B. Okay? This is the set of predecessors of some element. Now, we proved that the domain is also an initial segment. There are two cases. This might be a proper initial segment or all of P. Let's pretend that it's a proper initial segment. Then, this would be also the set of predecessors of some element, okay? But you see, F is an ordered isomorphism. In this case, since F is an ordered isomorphism from the domain of F to the range of F, since this is an isomorphism, we would have AB in F. Okay? Why? Because F is defined like this. F is defined like this. If the predecessors of two guys are isomorphic via something, then this ordered space is supposed to be in F. But that's a contradiction. Because, which is a contradiction, because, for example, B is in the range of F, but range of F is the predecessors of F, okay? A predecessors of B, sorry. So let me put this in parentheses like this. The reason I put this in parentheses is not that this is supposed to be a side remark. I'm just doing the following. I know that this is an initial segment. There are two cases. It's either a proper initial segment or all of P. Pretend that it is a proper initial segment. Then we get a contradiction. Therefore, the domain of F is actually all of P. So domain of F is all of P. In this case, F inverse from Q to, in this case, F from P to the predecessors of B is an isomorphism. And so, which item was this? P is isomorphic to an initial segment of Q. Third item in the statement. So we are in the second case of the statement. Okay? So if this happens, then P is isomorphic to an initial segment of Q. And you can guess that in the third case, the symmetrical thing will happen. Case 3. Now, domain of F is different than P. So I'm just going to write this down. I'm not going to prove this because it's the same proof. In this case, Q is isomorphic to a proper initial segment of P. So imitate the proof in case 2. Okay? It's just like this, except you flip the whole picture. Now, you argue that the range is an initial segment. There are two cases. Either the range is the whole thing or it's a proper initial segment. Just like this, argue that it cannot be a proper initial segment. Okay? You simply change the places of P and Q. Argue that in this case, the range cannot be a proper initial segment. Otherwise, we'll run into the same contradiction. So the range is actually the whole thing. In this case, Q is isomorphic to an initial segment of P by F inverse, okay? So, do you want me to do the last case? It's just like this, the symmetrical argument. Now, we have proven something very important. If you have two well-ordered sets, either they're isomorphic, or this sits inside this as an initial segment, or this one sits inside this as an initial segment, okay? This is really important, because in future we're going to use this. For example, we're going to say that we're going to say things like every set has a cardinality. How do you show that? There are well-ordered sets called ordinals, and by axiom of choice, we're going to say that every set can be well-ordered. So when you pick an ordinal, either one of three things will happen. Either this ordinal and this set will be like isomorphic as well-ordered sets, or this will sit inside this, or this will sit inside this. And by some wizardry, we're going to show that there's always supposed to be an ordinal which is isomorphic to this set as a well-ordered set. So there will be a bijection between them, and using that bijection, we will be able to define the cardinality of a set, and so on. So this will be used in future. That's the point. This is important. Any questions about this? Now, what this proof shows us, besides the statement itself, let's go back to the idea from which we derived this proof. If you have two well-ordered sets, then if there's an isomorphism at all, then that isomorphism should send this element to this element if their predecessors are isomorphic, okay? I'm not saying that any order preserving map between two well-ordered sets is it's supposed to look like this, because, for example, take natural numbers with their usual ordering, 0, 1, 2, blah, blah, blah. Again, take natural numbers with the usual ordering, shift everything, x goes to x plus 1. This is an order preserving map. But the predecessors of 0 is not isomorphic to predecessors of image of 0 in this case. I'm not saying that every order preserving map looks like this. I'm saying that if you have two isomorphic well-ordered sets, the isomorphism between them, it's supposed to look like this. It's supposed to send this element to this element if their predecessors are the same. I'm kind of saying something trivial, but it's important. This is one of those things which is like very obviously clear, but it's actually really useful. Anyway, questions? Now, we can talk about well-founded relations in the last 12 minutes, and we can introduce the axiom of foundation. Think of well-founded relations as, what's the property that makes a well-ordered? The property that every non-empty subset has a least element, right? A well-founded relation is simply a relation which satisfies that. We don't expect it to be an ordered relation. It's just supposed to satisfy the property that any non-empty subset has a minimal element with respect to that relation. What do I mean by minimal? You'll see this in a second. So, well-founded relations and the axiom of foundation. Definition. Let E be a relation on a set X. Okay? E is said to be well-founded if for all non-empty subsets of X, maybe I should write this more symbolically, because otherwise it's going to be too long. For all subsets, if the subset is non-empty, then there exists some M such that for all S in M, S is not related to M. a relation itself to be well-founded if the following happens. You pick a non-empty subset. Whenever you have a non-empty subset, you can find an element to which there are no elements related, okay? For example, if you have a sequence of elements like this, this is related to that, this is related to that, this is related to that, this is not well-founded. So being well-founded is the same as there is no infinite descending sequence, okay? Because if you take the set of these guys, then you cannot make this happen. If you choose your M to be the set of A, B, C, D, you cannot find such an M. Now think of this as like, interpret this E as an order relation, okay? Pretend that this is an order relation. What this says is every non-empty subset has a minimal element, okay? But I'm allowing E to be any relation. It's not necessarily an order relation. I can still define minimality for an arbitrary relation. There's no problem. Now, this is the definition of a well-founded relation. Is this understood? By the way, some books might define this in a different way. Like, according to this definition, no reflexive relation is well-founded. However, you can just play with this and say things like, for all S different than M, in which case reflexive relations can be well-founded. So I'm just going to stick to this definition. So what are examples of this? Any strict well-ordered relation is well-founded. Because that's literally what being well-ordered means, okay? Every non-empty subset should have a minimal element. Okay. Now, for various reasons that I'm not going to explain at the moment, we want the membership relation on a set to be well-founded. I need more chalk. Okay, I'm going to use orange because I ran out of white. No, there's a white chalk here. Now, do you remember the membership relation on a set? If you have a set X, the membership relation on it is the set of the ordered pair is the set of ordered pairs AB, such that this guy is a member of this guy. Now we want the membership relation to be well-founded. The reason for this is, okay, actually you can work, if you want, you can ignore the axiom I'm about to introduce. There are set theories without the following axiom that I'm going to write down. But it's common practice to adopt this. Again, I can give you technical reasons, but at the moment you're not at a point where you can understand the technical reasons, so I'm just going to ignore that. I'm just going to say that we want this to be well-founded, okay? And as a consequence, we won't be able to find sets that go like this. And another consequence will be that there are no sets which are members of themselves, okay? So I'm going to write down an axiom which is going to prevent things like this. There will be no sets which create loops like this. A is a member of B, B is a member of C, C is a member of A. Because if this could happen, then if you take these three sets, you see this relation, the membership relation, is not well-founded on that set. So requiring this to be well-founded would prevent such things from happening. And that's something we want. So we're going to introduce an axiom which guarantees that the membership relation is well founded. So axiom 8, the axiom of foundation. As I said, if you want, you can just assume the negation of this. Indeed, there are set theories where you negate this. There's Axel's anti-foundation axiom, which literally says the opposite of this. But it's like, okay. The other axioms, I gave motivations for all those, for all other axioms, right? This one, like, think of this as, I can't find a nice analogy to describe this. Just assume this, okay? This is an axiom. Just assume this. I'm not going to give you any motivation for this, unlike the other axioms. The other axioms has very nice motivations. This one, you simply assume it. You assume it because I'm telling you to do so, okay? If S is a non-empty set, then there exists an element of S disjoint from S. That is, for all S, if S is not empty, then there exists S and S such that the intersection is empty. Now, in this form, it doesn't say that the membership relation is well founded, or it doesn't say that no set can be a member of itself, but it implies those, okay? So let's prove that in the remaining 2 minutes, I guess. 3 minutes. Let's prove that the membership relation is well founded on any set. Theorem or proposition. For any set X, the membership relation is well founded. Proof. Now, if X is empty, then the membership relation is empty. So this is well founded. Okay? There's no problem with that. Assume that X is not empty. Then, by the axiom of foundation, by axiom 8, there exists little x and big X such that the intersection is empty. Okay? Now, I claim that this guy is a minimal element with respect to the membership relation. We claim that there is no I'm missing something. I don't want to do that. I don't want to do that. I want to show that something is well-founded. What does well-founded mean? Any non-empty subset should have a minimal element with respect to that relation. So I need to pick a non-empty subset. So let's pick a subset which is then empty. Now I'm going to use the axiom of foundation. By axiom 8, there exists little m and m such that the intersection of these guys equals empty set. So this element of this set is disjoint from the set itself. If it were the case that this guy is not minimal with respect to the membership relation. Now, there are too many epsilons here. This is the actual membership. This is the name of the membership relation. If this were the case, if there exists some element of m such that this is related to little m, if this were not minimal with respect to this relation, then, well, by definition of the membership relation, we would have this. And so x would belong to the intersection which is empty, which is a contradiction. Okay? Thus, there is no member of m such that x is related to little m under the membership relation. This is literally what it means for this membership relation to be well-founded. Now, because this relation is well-founded, we can prove all those things, like no set is a member of itself. You don't have loops like A is a member of B, B is a member of C, C is a member of A. You can't have loops like this. You can't have infinite decreasing sequences, things like that. As I said, you don't have to accept this axiom, but here is like one reason you accept this. Ignore this axiom. Towards the end of the course, we're going to construct something called the von Neumann cumulative hierarchy. And all sets in that hierarchy satisfy this. For those sets, this is well-founded. You don't ignore this axiom. For those specific sets, you can show that this is well-founded, okay? Sometimes people call it the hierarchy of well-founded sets as well. Now, the set theory is supposed to be a foundation of mathematics. And it turns out that all the mathematics we care about can be done just using those sets for which this is well-founded. So if I take all the sets for which this is well-founded, those sets suffices for me to do any kind of math I want. So then I should do the following. It's like, how should I explain this? Well, I'm trying to jump, and with my shoes on, I can jump higher. Because I want to jump higher, I can just integrate having shoes as a part of the act of jumping, okay? So I don't need to consider jumping without shoes if I can jump higher with shoes. It's kind of like this. If all the things I want to do in mathematics, I can do those with sets for which this relation is well-founded. So why should I not assume that for all sets this is well-founded? So this is not this is not a necessary axiom, but it's just we're basically restricting our attention to those nice sets for which this is well-founded. As I said, we can just drop this, and set theory would work fine. If you restrict yourself to those sets for which this is well-founded. But then I have to say things like, I want to prove something about sets. Then I have to just use the phrase, I'm assuming that these sets satisfy this property and these sets satisfy this property, then blah, blah happens. I don't want to do that. I'm simply going to assume that this is true so that everything works out nice, okay? But this is not crucial. Indeed, you can just take a look at Axel's anti-foundation axiom where the negation of this happens, and you get a cool set theory as well. I mean, it's As an intellectual activity, it's nice to play with those, but why would you assume the negation of this? Why would you want sets that contain themselves and things like that? Aside from the fact that like they create a nice playground for logicians. Anyway, so next lecture I'm gonna prove two consequences of this, and then we're gonna start constructing natural numbers, okay? We're gonna learn what natural numbers are. At the age of, how old are you in general? 20? So after 20 years, you actually now will learn what natural numbers are. So I'll see you on Thursday.